So hi everyone, and welcome to the second episode of the SharpestMinds Mentee webinar. Today we actually have a very special guest. We have Simon, who's going to talk about SorterBot. And Simon is a chemist from Hungary who turned to software development 3 years ago, and he built this project to showcase his engineering skills. So I'm going to hand the floor over to Simon, who's going to present, and then we'll open the floor to questions afterwards. So thank you, Simon, for being here, and thanks everyone for being present today.
Thank you for having me. Hello, guys. Welcome all. So I like to talk about SorterBot. It's basically a robotic arm equipped with a magnet and a camera, and it's able to automatically pick up little metallic objects and put them into separate containers. And when I got started, I took a bit of more general approach. So I built a cloud service which is able to connect to multiple Raspberry Pis, and you could actually connect any kind of sensors and actuators to these Raspberry Pis, and you could record some data and send that to the cloud, do any kind of data processing, can be with deep learning, can be without, and you can send back the commands to the Raspberry Pis, and the actuators can act on them. And a specific example of that, what I built, is this SorterBot that I will talk about now. So basically, this is how it looks. This is a robotic arm that I ordered from China. It's a very cheap one, not the best quality. And I had some problems with that. I will get to that later. So this is basically controlled by servos. There are two servos on the sides, one here and one on the top here, and on the top of it there is the electromagnet and there is the camera, and here you can see the Raspberry Pi. So this is the electromagnet and this is the camera. So first I will show you a video of how it works, and then I will explain what is happening and how exactly it is doing that. So here is the video. So right now, I put only one container. As you can see, first it moves to initial position, and then it takes a couple of pictures. First, I wanted to do it with a video, but because of the poor build quality of the arm, as you can see, as it moves, it's quite shaky. The pictures would be very blurred. So this slows it down a bit, but at least it's working properly. And after it took the picture, it uploads them to AWS, where the processing takes place. It also takes a bit of a time because I'm doing inference on CPU, which is very inefficient. And now it's done, and it's moving. There picks up the objects and moves them to the container. So it needs a bit of help because the magnet is too strong, so otherwise it wouldn't fall down. And as you can see, the build quality is, again, not the best. So I will show you one more video. Sorry, this is the same. Yeah, this one. So now there are two containers and 5 objects. And as you see, there are 2 screws and 3 washers. So they are looking pretty different. And it will recognize that there are 2 containers, and it will group those 5 objects into 2 groups based on how they look. So I'm expecting to put 3 washers in one container and the 2 screws to the other one. And on the background, you can see it on my laptop. There is a control panel that I can use to control it. I will talk about that later too. So it basically did it automatically, so I didn't input anything about how many containers are there, so that's also automatic. So this project includes 5 repositories. Originally, I planned only 2, the SorterBot Cloud and the Raspberry, and then I added later on 3 others as new ideas came up. So SorterBot Cloud is basically responsible for taking an image, running a deep learning inference, in this case, doing object recognition, and then saving the results, the locations of the bounding boxes, into a database that can be later on used. And SorterBot Raspberry is a Python script that is running on the Raspberry Pi. So that controls the robotic arm, controls the 4 servos, takes the pictures from the camera, uploads it to AWS, and also turns on and off the electromagnet as it's needed. So the control panel is a web application with the Django backend and the React frontend, and that displays the logs as they are happening, so they are being pushed to the front end. I used WebSockets to achieve that, so the whole thing is totally real time, and you can also see the status of the robotic arms, and you can click a button to start a session, and then it will take the pictures and do the rest. So the SorterBot Installer is a set of utilities that automates the process of deploying this whole solution to AWS. I will talk more about it later, why is that needed. And the LabelTools is a Python OpenCV application that is help to facilitate the labeling the dataset. So SorterBot Cloud, the first one, a bit more details about it. So it uses the Detectron 2 framework from Facebook AI Research, and that is built on top of PyTorch. And I use that because it provides a lot of network architectures that I could choose from, and also a lot of convenience functions for training and for inference as well. And then that network outputs the bounding boxes, which are being saved to a Postgres database that is running on AWS RDS. And the images that were used for the inference, just for later reference, they are saved to S3, so they are not necessarily needed for the rest of the process. But if I want to check it, what the network worked from, I can later on recall that. And after that, there is a second neural network that is being run on the individual objects. So I cut out the pixels within the bounding boxes, and I input those small images to the second neural network, which creates the clusters. So that's how I decide which object belongs to which group. And that's the K-means clustering algorithm is that doing this this job. So that needs the number of clusters, and that is because the object recognition network also does a classification. So it does a binary classification, and it tells that it's an object or a container. And then I just simply count how many containers are there, and that's going to be the input for the K-means. And the other input are the vectors, which are basically 512 long vectors. So they are 512 float numbers, which are representing the small images, so the objects themselves. And based on that, I can have a pretty good idea which object looks similar. And after all of this is done, this repository also includes some functions that are generating the commands that can be executed directly by the Raspberry Pi. So they are sent back, and then they are executed. So the SorterBot Raspberry repo, that's the Python script that is running on the Raspberry Pi, and that controls the servos with PWM, is pulse width modulation. That's I don't want to get into details, but it's basically a pretty standard way of controlling servos. So there is like a cycle, and depending on how big percentage of that cycle is logical 1 is, as opposed to logical 0, that determines where the servo will move. And when I was using the default library for Raspberry Pi to control the general purpose input-outputs that are connected to the servos, I had some problems, and namely that it's using a software-based timing. And the problem with that is that it depends on the CPU load. So for example, if the CPU is doing some other stuff, for example, uploading things to AWS, then the timing can be off. And that's why hardware-based timing is appropriate here, and the PIGPIO library can provide that, so that improves the accuracy a lot. And also I needed, because the way the PWM works is that you give a command and the servo moves to that angle immediately as fast as it can. And in the case of the robotic arm, that's not really what I want, because then the robot will move very fast and start and stop very abruptly. So that will result in a lot of shaking, and that's not what I wanted. So I had to do a slower movement, and for that I had to do an interpolation. So create so basically do a linear. First I did a linear interpolation that was also not the best, and that's why I applied sign smoothing. So on the next slide you can see the results. So on the left, as you can see, it moves pretty fast and shakes a lot, so that's not so nice. In the middle, linear interpolation effectively slows it down, but on the end you can still see that it shakes a bit. And with sign smoothing, that shake is almost completely eliminated. It's still not perfect, but much better than what I started with. Okay, so this is the solution overview. I will show you in better quality. Yeah, so I have it here in Figma. So basically, when a session is started, the Python script on the Raspberry Pi will move the arm to initial position, and then it starts to rotate the base of the arm. And at every predefined angle, it will take, send that image to the cloud repository, and then there it will be processed, converted to bounding boxes, and saved to the database. So this happens for all of the pictures. And when a session is done and all of the pictures were sent, a special command is being sent, and that is picked up by the vectorizer. So that is first loading the bounding boxes from the database, and then it converts them to polar coordinates. Because originally every image has the bounding boxes defined in their own coordinate system. So I had to bring them all into the same coordinate system, and that's polar coordinate system is the best for that, where the origin of that system is the middle of the robotic arm. And then after I converted all these coordinates to a single system, then I can filter out the duplicates, because most of the objects are showing up on multiple images, and obviously I just want to pick them up once. So all the duplicates are basically averaged, and then I will move the robotic arm in that averaged position. And after that, for every unique object, I will crop the pixels from the original image and convert them to a tensor and create a batch. And that batch will be run through the second neural network, which creates the embeddings that I was talking about before. And that's the one input for the k-means algorithm, and the other is the number of containers that came back from the classification. And that k-means algorithm outputs pairs, basically which item belongs to which container. And then the last function creates the comments from that, and those are sent back to the Raspberry Pi, where they are being executed one after another, and when all of the images were moved to their containers, then the session ends. Okay, so that was not all, but because it's quite long, so I want to pause a bit. If somebody has questions, then I'm happy to answer them.
So if anyone has questions, you can either number one, type it in the chat, unmute, or you could use like the raise hand function. So whichever is more convenient for you guys.
I have like a million questions, but I'm just gonna pause until everybody else has a go here.
I actually have a question. So I'm kind of curious. I know you talked about this a bit earlier, but just in terms of like the actual hardware, like the robotic arm, when you built that, did you have to build everything from scratch, or like how much of the parts did you buy versus how much did you build to put it together?
Yeah, so I built a kit that I was supposed to assemble it by myself, and it cost something around $120. So that's a very, very low quality thing. And and that was one thing, that the instructions were all in Chinese. But the biggest problem was that those parts that were on the photos were not really included in my kit. And I thought I got a different model, but that was also not the case. So basically, I got a mixture of different models. And I had to like drill a few holes here and there and bend them a bit and like make even a few smaller parts, but on the end it worked out. So this is normally like a whole kit. And I also had to replace one servo because it was just totally terrible.
Yeah, that's super cool to know. Yeah, thanks so much for explaining that.
I did have a quick question. I love the algorithm side of it, the k-means bit. Maybe it's just that I've never worked with this kind of problem before with the combination of robotics and computer vision, but the k-means strategy was so cool. Could you unpack that a little bit more? Like, because my understanding right now is, so you take a picture, the first thing you do is you're trying to figure out, okay, where are the objects so that I can then like kind of crop them out. And that's step one. The first algorithm is just like, that's the ResNet 50. I think you mentioned, where are the objects in general? Then once you crop them out, you kind of go, okay, what does this object look like in latent space? So I'm going to put that object through another neural network, get a latent vector, and then you cluster those vectors with the number of clusters, the k value being determined by the number of buckets, which you separately. That's so cool. Okay.
Yeah, that's right. So basically, the object recognition network does two things. It first localizes every object, and then second, it tells if it's a container or if it's an item. And then I just simply count how many containers were found, and that is one input for the k-means. And the second is just basically the pixels. So the pixels are they are a bunch of numbers, and they are represented. They are transformed to a much smaller quantity of numbers, which are more or less still representing the original distribution of the pixels. So they are also representing how that item looks, and that's needed to make the k-means feasible and faster to execute.
That's really cool. Okay, last question, just for now, I promise, because otherwise I'm going to yammer on. But I'm really curious about failure modes. So you make this k-means clustering algorithm. You've got a dimensionality reduced representation of every object, and then you're kind of telling the algorithm like cluster things that like look similar, that are closer together in parameter space into the same bucket. I'm guessing like there might have been some counterintuitive clusterings that you observed, maybe not, but I was just curious about that.
Yeah, definitely. So I didn't really get into that problem very much. So it could be definitely much more sophisticated. So for example, I could create a neural network that is more like trained for this, and then I could weight in like I want to separate them based on structure or texture, based on color, based on shape. So I didn't really do that. So I just simply do a vector with completely general neural network. It was trained in an image net, so I just it works out of the box. So probably if I would use items that are like more or less similar, then it might produce some unexpected results. Or for example, if I have like so now I had two types of items and two containers. But if I have like three types of items and two containers, or two types of items and three containers, then it might do some stuff.
Yeah, interesting. Almost like you could have almost like a betting game where you put a whole bunch of items in front of it, and you're like, okay, which items are going to get clustered together? Like, anyway, sorry. Awesome. Thanks so much.
I don't see a chat. If anybody wrote some questions, then maybe you could read it out.
So I had a question about scoping, because there's so much complexity here. And one of the key skills that we see over and over again being required is the ability to scope that complexity. So I'm just kind of in general wondering how you thought about that. Were there times that you had to like re-scope things, or they were getting out of hand, or just in general? Yeah, your thoughts on that.
Yeah, actually, I added a lot of features as I went. So this, what I explained so far, that was the original plan, and what is coming, that I added later. So the control panel, deploying the whole thing to AWS, and I focused more on that because I wanted to make this like an actual product that people can use. So not just like an experimental project. So I focused less on the deep learning part of things, and I focused more on deployment, on testing even, and making it easy to use. So on the end, you will see that it's pretty easy to use. So you can deploy it basically running a single script, and that's it. And it has like a lot of resources in the back that are being made to work together.
See, that's fascinating to me, because if I'm interpreting correctly what I think I just heard you say, which was you focus things down to like basically move forward and kind of build momentum into this project, and you saw the scope through the lens of like building something useful, like
Yes.
very product oriented, and that kind of constrained things going forward and allowed you to generate momentum.
Exactly. For example, that was quite surprising for me when I did the neural network training. That I thought that I'm going to spend days or weeks on fine-tuning hyperparameters and stuff like that, and it was absolutely not like that. So first try and it works, and the training literally took 5 minutes. So I just labeled the data set, first try, and bam, it worked. So of course I could increase the accuracy, because it could go up like 5%, maybe even 10%, but it was just not needed because this also because of the taking the average of multiple localizations of the object, and also as you can see, this magnet is pretty big. So if it's off by 2-3%, it can still pick it up.
Got it. Thank you for sharing your thoughts on that. Really appreciate it.
Just as a last quick note with that, and thanks, Ali, for those questions. I think those are so important, because like, you know, everybody's watching this. They have their own version of this problem that doesn't involve robotics, that doesn't involve all the, maybe even the deep learning. But I think there are a lot of lessons that cross over, including like just focus on getting something that works. And to your last point about like these objects are like, they're pretty big. So once you get to within a certain accuracy, like declare victory and move on. That's such a constant theme in all these things, like not when to fold, know when to declare victory. And anyway, really cool that you put so much thought into that too.
Okay, any more questions before we move forward?
I don't see any questions in the chat right now, but yeah, if you guys have questions, we're going to be stopping again later in Simon's presentation for questions after as well.
So let's see SorterBot Control. That's so the SorterBot Cloud name is a bit confusing, because this is also running in the cloud, but that was not originally planned, so I just later on added it. So this is for control and monitoring. So it has a React frontend, Django backend, and it uses WebSockets both for communications between the frontend and the backend, and between the backend and the Raspberry Pis. So as the Raspberry Pis are executing different commands, the logs are sent directly to the backend, which are saved to the database and immediately pushed to the front end. So you don't have to refresh the page, they are showing up real time. And also there is a status button for every robotic arm, and that can have 3 states. Basically, when it's not blinking, then it's offline, it's not communicating with the control panel. When it's blinking yellow, that means that the robotic arm is checking into the control panel, but the robotic arm is not connected to the inference engine or the SorterBot Cloud. And when it's green, then it all works. And the other thing that it can do, because so the control panel can run in an EC2 instance that is covered in AWS's free tier. But the inference engine needs a bit more compute, and that is not, so that is paid, obviously. And the ECS cluster can be scaled up and down. So I use that Python SDK to write some commands that basically you can press a button and then it will scale it down to 0, so you are not paying. And then you can just press another button, then it will scale it up, and then you wait a bit and wait until your cluster is provisioned, and then the inference can be turned on. And also you can start the session by clicking on the appropriate buttons, view the logs, and also there are landscapes stitched together from the images that are recorded. And then that is a way to verify what your robotic arm actually did. So you can see a before and an after image. And you can see as the items were moved to the container or not. So this is the UI, this is how it looks. So on the left side here, you have a list. I just have right now one, but you could have multiple arms. You can see the arm ID, and there is a timestamp when it checked in last time, because if a Raspberry Pi is running the script, it checks in every 3 seconds. I will explain it later how that works exactly, and then it checks in with the status of, and that's what blinks that status indicator, which is this one here. And there is this play button which can start the session. And here next to it, you can see the sessions, you can see the status that it's completed, and there are the logs separated by logical groups. So there's like a command execution, command generation, and those numbers like 1,000, 1,200, things like that, those are belonging to a specific position, because these are the pulse widths that were sent to the servo when it moved to a separate angle. And one image belongs to one position, and there is like a bunch of logs that belongs to that. And also the images here on the screenshot, they are not generated yet, but I will show you later on how they look. And yeah, on the top here, you can log out, because you need a user account to log in to see the screen. And right now, this when I took the screenshot, this is running in development mode, so you can see that Cloud is running on localhost. But when this is in production, if it's offline, then it shows you a button that you can click and start up the cluster. And if it's running, it will display the IP address of that cluster. And actually, that's also very useful feature of this control panel, because normally when you stop the cluster and you restart it, you get a new IP address. And you would have to configure all of your Raspberry Pis every single time when that IP address is changing. But the control panel can retrieve that address, and when an ARM checks in and that IP address is wrong, it can send back the new one. I will also explain this later on how it works exactly. And here, this is a picture that was stitched out from multiple images. As you can see, it's a bit blurred here and there. So this is using a built-in algorithm from OpenCV. It's not the best. Sometimes it's not not finding the overlap from all of the images. That's why I had to put down that ruler. So that helped a bit, because my desk was too similar. So it was not distinct features that it could use to make the stitching. Okay, so this is how the whole system works. So let's start in the beginning. Just for context, as we are moving from top to bottom, that symbolizes as time moves forward. And these lines are the different parts of the software that are running. So this is the Raspberry Python script that is running on the Raspberry Pi. This is the inference engine. This is the control panel. And this is the storage. This represents also the storage buckets and the Postgres database. And this is the user interface that displays different things. So first, when a session is started, the Raspberry Pi does a ping pong. So it checks if the IP address that is configured, so using that IP address tries to connect to the inference engine. If that is successful, then it skips forward here. And if it's not successful, it sends a query to the control panel. And that control panel gets the current or latest IP address using the Python SDK of ECS, and then sends back that IP address. And then it retries the ping pong, and the result of that will be sent to the control panel. So this can be a success or a no success. If it's a success, then the status LED will blink in green. If it's not a success, it will blink in yellow. And then when this status arrives to the control panel, first of all, it checks if that ARM is already registered, and if it's not, it will register it and add and display it in the list of the ARMs. And then it will push the status to the front end, and it will blink the LED. And because every ARM checks in every 3 seconds, so I found it's more feasible to start the sessions not in a direct way. So if you click the button, it's not sending an event that starts the session, but adds the ID to a list which Raspberry Pis should start a session. And when this function is executed, it checks if the current ID is in that list. If it's not, it sends back that no session should be started. And if it's there, it takes it out and sends back that the session should start. So then it comes back, it can be a yes or no. If no session should be started, it waits 3 seconds and executes this. This is, I call this the heartbeat sequence. And then if a session should be started, then it sends a post request to the control panel, to the Django backend, and that registers the new sessions, and that consequently will show up also on the front end. And then the ARM will move to positions, take the configured amount of pictures. That was 5 in that video that I showed you. And then it will send these images to the cloud service. I wrote here the thread pull executor that submit, because if I send if I send these images in a synchronous manner, then the whole execution is stopped until that image is actually uploaded. So that wastes a lot of time. So I spawn different threads, and those are taking care of uploading the images. And in the meantime, the execution of the ARM control and the ARM can move forward. And so when one image arrives to the cloud service, it will process the image in the way that I showed you before. So it will generate the bounding boxes, all things like that, and then insert the results to the Postgres database. And then because this stitching together the images, and also this is not stitching yet. So this is just saving the image to disk and uploads it. Also, this is done in a separate thread because it's not in the critical path, so there is no reason to hold the whole process while we are doing this upload. So this also saves a considerable amount of time. So then this sends back a success or no success, and the Python script on the Raspberry Pi waits until all of these all of these results come back. So if all of these are completed successfully, so if they are not completed, then the session ends because there was some error. And if all of these are completed successfully, then it sends a get comments of session request to the cloud service. And what it will do in as a response, it will get the bounding boxes from the Postgres database and run the vectorizer network, the k-means algorithm, all things that I explained before. So this is doing it here. So object to polar coordinates, then filter out duplicates, run the vectorizer, generates the comments. And in the meantime, it on a separate process, because it's not a thread, it's a process, because this is a CPU bound task. So stitching together the images is a CPU bound task. So I spawn a different process, and in the meantime, while I'm running the vectorizer network, this stitching can be done. And from that process, the stitched image will be saved and displayed on the front end. So after this is done, the commands are being sent back to the Raspberry Pi. Those are being executed, and after that it makes another session, but it's not really a session, it just takes the images so they can be stitched together, and it can generate an after landscape. So you can have a before and an after landscape, and you can compare what your ARM actually did. So this is basically the same thing like above, and then after this command was sent, then it resets the ARM to the original position and ends the session. Okay. So next repository, the LabelTools. So this is the Python application that I did to facilitate labeling process. So normally I would have a bunch of images, probably like 1,000 of them, and I would have to draw bounding boxes around the objects one by one. I didn't want to do that, so that's why I built this software. So what it does, instead of taking these pictures one by one, it takes a video. And it takes a video while the arm is moving. And instead of labeling every single picture, I have to label once per object per video. So for example, I have 15 objects and I take a video. I can grab 15, 20 images from that video, and I have to label them only once, not 15 times. And because I know the exact trajectory as the arm moves, I can calculate, if I know a few constants that can be measured, I can calculate the positions of the bounding boxes on the rest of the images that are grabbed from that video. I will show it later on a bit more visual way, so it will be more clear. And so that seemed like a good idea, but due to the poor robotic arm quality, I couldn't make it work, because as the arm was moving, the robotic arm was shaking and the pictures were totally blurred. So I had to do it in a bit different way. I was still recording the video, but in the same intervals. I moved the arm a bit, I stopped, I waited until it stopped, and then there was a perfect position to grab an image. So I basically took a video and I stopped like 10 places as it was rotating, and I made sure that the pictures are grabbed in that in those moments when the arm is actually not moving. But because even that was not working the way I expected, so those even distances were slightly uneven. Sometimes it was a bit more, sometimes it was a bit less. So it happened a few times that that the captured images were blurred. So I had to build another tool that I could use to verify every image that it was actually properly captured or not. So I was basically looping through all the images and I was pressing plus and minus to keep the image or not. So that was a pretty fast task. So and at the bottom you can see here is how much time it took to do all these things. So I recorded 5 videos around 15 minutes. Then it took me 45 minutes to label them because I had to play around with a few parameters to get it right, and then 15 minutes to verify them. And then on a GPU, I was running the training for 10 minutes and I had a satisfactory results. Okay, so this is how it looks when I'm drawing the bounding boxes. And that slider that I'm pulling left and right, that is the tracker of the video. And as you can see, if the radius and angle, the other two parameters are set properly, then the drawn bounding boxes are nicely following the objects on the picture. So as you see, the bounding boxes are not rotated. It could be better if they would be rotated. That would be also possible. It could increase accuracy quite a lot, but it's just not worth effort because it works. So I didn't want to spend more time fixing something that is not broken. And here you can see what happens if I'm playing around with the radius and angle. So then I basically had to draw a few bounding boxes and draw that sliders to those positions where they were like matching the objects. And once I got it, I had to label them all, and that's it. And you can see that there are a few bounding boxes, the big ones that are red. So those are the containers. So this is how I created the training data for the classification as well. So if I just drew a bounding box, that was considered an item. If I drew a bounding box while holding down shift, that was considered a container. And the bottom two sliders are the export, offset, and interval. That was to set which images should be grabbed from the video. And to help it visualize it, I made it in a way that when the video is playing, all the bounding boxes are turning to white when they are being grabbed. So I could make sure that the bounding boxes are grabbed when the arm is actually not moving and it's stuck and it's not blurred. Okay, and this is a picture that came back from, so these bounding boxes are inferred by the neural network. And also there are the confidence, like 94%, 93%, 87%. So it's pretty high confidence, and I think it's satisfactory, and especially because the arm was moving to the center point of these bounding boxes. So as you see, they are well within the range of actually grabbing it. Okay, and this is the SorterBot Installer repository. So first I did a manual setup. I had to set up, like, I think 8 different services in AWS, also a lot of secrets, lot of different stuff. So I did actual manual setup guide, and I wanted to make very accurate. So I asked my girlfriend to actually try this out, and it took her 3 hours. She's not a coder, she's not really into this, but she was able to do it based on that, but it was 3 hours. So I figured that this has to be automated because this is just way too long. So I automated the process mostly using AWS CloudFormation that was responsible for deploying the different resources. But there were a few things that were not supported by CloudFormation and AWS CDK, and those were the security credentials. So I used a bash script that was using the AWS CLI to generate these credentials and save them and arrange them the way it should be. So the way it works, that you set up 5 environment variables, your AWS account ID, a GitHub username and access token that is needed for the CI pipeline that is deploying the inference engine. And then you just make up a username password that you want to use for Django when you are logging into the actual application. You run the deploy script, wait 30 minutes, and it's done. So it's much more friendly than doing all that misery in the manual way. So what it does, it first uses the CLI to generate all the AWS access policies and secrets and saves them to a parameter store. Then it deploys the ECS Fargate cluster for the inference engine, an EC2 instance for the control panel. I think it needs 3 or 4 storage accounts and an RDS instance to run the Postgres database. And after that is done, it also triggers the GitHub Actions CI pipeline, which pulls the code from the GitHub repository of the SorterBot Cloud, builds the Docker image, pushes it to Elastic Container Registry, and then updates the image that is being used by the cluster. So in that sense, if you are retraining your network and you want to use some different weights, you don't have to redeploy the whole thing. So all you have to do is to upload it to S3, go to GitHub, create a new release, which is 2 clicks, wait a bit, and it automatically updates it. So that's really useful because deploying all the resources is pretty tedious, even if you are automating it. So you don't want to do it multiple times a day. Okay, so also second break for questions. If anybody has something, I'm happy to answer.
I think a lot of this is a little over my head, and by a little I mean a lot, because I don't know anything about robotics, things like that. But so one thing that that I was wondering from a higher level kind of picture side of things is, like, have you thought about maybe like monetizing this? I mean, it's actually like I don't know if you're familiar with Kindred AI, but there's a company that does something along the spec. Okay, yeah, you might want to like reach out to them, see if they're hiring, because this is so in that area that, anyway, if you're curious about them, let me know and we can chat.
Yeah, actually, I already have a job, so that's not needed anymore.
Oh, so okay, well, even better.
Yeah, but I know about them. Came across it's pretty similar what they are doing, but this cannot be really compared to what they do. It's completely different.
Yeah,
yeah, like really profitable.
Yeah, just as a general rule, like your project doesn't have to accomplish the exact thing that a company is doing in order to but the fact that you've considered all these problems, I think it's so compelling and it's really impressive. How long did it take you to do this, by the way, end to end?
Yeah, like a lot. I started to work on it end of January, and I got to this level by end of May, I think. It was, I also tracking the time that I was doing, it was around 600 hours.
That's still pretty, like, honestly, that's pretty quick for the amount of stuff that you
yeah,
back though, right? In robotics before? Or?
No, nothing. That's actually basically all of this thing was completely new for me. So that's why that's why I did AWS, because I wanted to try. Never worked with AWS before, so that was a good opportunity to do this thing. Never worked with Raspberry Pi, never worked with robotics at all. Yeah, Python and React that I knew from before. Also never worked with WebSockets. So basically that was I considered it an opportunity to learn new things and try new stuff. So I didn't want to go that way that I already know. That's
amazing. I'd love if you have a list of resources you use to pull this off. I think that would be fascinating for especially people who look at part of your chain and go, oh, like I'd love to be able to do that little part of it and figure out what resources were helpful there, because you've uncovered so much here. This is really impressive. Yeah, like nothing specific. So I just like as the problems occurred, I solved them the regular way, mostly Stack Overflow. So most of this stuff is on Stack Overflow. Or I didn't really take any courses for that or whatever. Like for example, Detectron 2 has very good documentation. So everything is written there, how to do the training. There are examples. So those are very useful things. Awesome. Well, thanks a lot for sharing this. It's really cool.
I have a quick question actually related to what Jaren was asking. So, and also like related to what you mentioned about kind of like the approach you took for the project. So in terms of like your tech stack, like what were the considerations that you had when you were selecting like your tech stack? Because I know you mentioned that you had worked with like Python, I guess like Django for your back end, and then React like in JavaScript for your front end. But like, what were you considering when you were like picking like what languages, platforms, APIs, and stuff to use?
Yeah, considering the language, I picked Python because I wanted to work with that and I wanted to get a Python job. So that was basically a way to show off my Python skills and also improve them, because obviously I learned a lot on the way. So I got to use a lot of features in the language that I never used before. And the front end part, I just used React because I like it. I used Vue and Vue as well. Angular I didn't, but that was not the focus on this project. So I just went the easy way. And yeah, but the communication protocol, I could achieve the same thing, a bit more tedious with regular REST calls, but I wanted to try out WebSockets, and because of the real-time nature of this project, it was also a good fit. So that's why I went with that. And AWS, like I said, because I never used it before, and I was curious how it is.
Yeah, thank you. I'm like learning a lot. I definitely like, it's my first time hearing of some of these things. So this is super interesting. And I'm just like really, excited that you're here. So thanks for sharing that.
No problem. So, but basically what is the last part will be about. Yeah, Jim? Say something.
Oh, sorry, I was clapping. I don't know. I don't know how to use the internet, Simon. Sorry.
Okay, sorry. Okay. So there is one big shortcoming of this whole project. It's not really scalable. I mean, that it has the potential to make it scalable, but at the current state, it's not. Because, for example, like I showed you before, that some parts are using multiprocessing, but that is only useful if you have multiple cores. And if right now in the Fargate cluster where I deployed it, it has only a single core. And also doing computer vision on CPU, that's not really the best idea. Definitely not the most cost efficient way. So and also because of the messaging part, so the control panel is a single instance, and that would have to keep an open connection with all of the Raspberry Pis through WebSockets. So I didn't try that, but my wild guess is that probably around above 1,000 Raspberry Pis, it would completely crap out. So in the last part, I didn't do that work, so it's completely theoretical. I just explored a few ways of how could I make this scalable to be able to handle like millions of Raspberry Pis. I mostly focused on the inference part and what solutions are there and how much would that cost. But on the messaging part, that would be definitely the way to use a message bus service. So it's basically like a tube where in one end all the Raspberry Pis are putting in the messages, and on the other hand the servers are taking it out. And then if there is a bit of overflow, then I could always scale up and add more instances to it. So that way it could handle like thousands or even tens of thousands or millions of Raspberry Pis. So yeah, so right now the object recognition is done on CPU, and it takes 5 seconds for an inference, and that's pretty bad. So when I took a look on the official benchmarks of the Tectron 2, they were saying that this network is supposed to do inference in 40 milliseconds. So that's like a huge difference. And mostly, so most of it is because it's done on CPU, but also I was doing it on full-size images, which is absolutely not needed. So I was doing it on something like, I think a full HD images or something around that, but 640 by 480 perfectly enough. And the other thing is that because this Docker image that I built for the inference engine, it included PyTorch and Detectron True as a dependency. It resulted in a huge Docker image, over 4 gigabytes, and that's also not really suitable for production. And a bit of price estimate here for 1 million requests. If we are counting at 5 seconds of inference time, it would take around 1,400 hours. And with the hourly price of that Fargate cluster, it would cost around $25 to infer 1 million images. And I will explore a few options of how could this be made cheaper. So a few quick wins is that first of all, just to reduce the input size, that immediately cuts the inference time a fifth. So that's quite nice. And instead of using a Flask server, there is a pretty new tool. It's called TorchServe. So that's basically a web server for deep learning inference. So that's the PyTorch counterpart of TensorFlow serving. I didn't use TensorFlow serving, so I don't know how exactly it compares to it. But the point is that I don't have to maintain the PyTorch and the Detectron 2 dependency. So I can just compile my network, neural network to a file which is around 300 megabytes, and that can be used by the TorchServe Docker image for inference, and I don't need to maintain all these dependencies. And that reduces the image size to 1.7 gigabytes, including the CUDA, which is needed for GPU inference. Without that, it would be around 700-800 megabytes. So that's also a quite big benefit. And on top of that, it has nice features like multiprocessing, which is not really going to be useful in case of GPU inference, but there is the opportunity for that, logging metrics and nice model versioning. So that's actually pretty cool. You can just send a post request to this web server, and that will register a new version of your model, and you can just swap it in production like that. You don't have to redeploy it. It's really cool. And it's also natively supported in AWS SageMaker. So I don't exactly know what that means, but that's definitely a big plus, and makes things much easier. So I was exploring things how to deploy this on Google, but that's not really the easy way. Okay, so first of all, I just wanted to make sure that it really makes sense to use a GPU. So the CPU inference time is around 1,000 milliseconds, and the benchmark inference time on GPUs, it's around 40 milliseconds. So that means the GPU is 26 times faster. But let's see what happens if we consider the costs as well. So I went just with the cheapest options. That's not guaranteed that those inference times will be the same. It's just a ballpark. So the cheapest GPU costs 40 cents an hour, and the cheapest CPU costs 5 cents an hour, so that the GPU is 8 times more expensive. So that means around the performance to price ratio is 3 times better with the GPU. But it can still change a lot because the inference times obviously define this, and they are just very rough estimates. So this is one option to deploy it to AWS SageMaker instance to a TorchServe endpoint. I just found this image in an AWS guide how to do this. So basically, the compiled image would be saved in an S3 bucket, and using a AWS deep learning image that would be pulled into a SageMaker instance, and the client could send requests to that instance, and it would do the inference. So see the benefits, the native TorchServe integration. So actually, it's much easier to make this work than it would be on Google, for example. And also, SageMaker has a really nice feature, elastic inference, and that means that I can choose, I can set the type or the amount of GPU acceleration that I have. Because, for example, if I would go with the smallest SageMaker instance that has a GPU, that includes 4 CPU cores and 16 gigabytes of RAM. So that adds a lot in costs, and most of it would be unused because I wouldn't use more than 1 CPU core for inference, and I would definitely not use 16 gigabytes of RAM, probably not even 4. And otherwise there will be just no way of not paying for these unused resources. So as you see, it also already reduces the costs a bit, but not a lot. But if I go with elastic inference, I can go with a much cheaper and much less powerful CPU and RAMs, and I can still have some GPU acceleration. So that reduces the total cost to $8 for 1 million requests. So it's almost 70% of reduction. That's pretty nice. So this would be another architecture. I came up with this myself because I also wanted to compare how is it to do the same thing on AWS and Google. And this would be one solution on Google using a Kubernetes cluster with GPU nodes. So basically, here it would work in that way that the Raspberry Pis are taking the images, they are uploading it to a cloud bucket. And that cloud bucket has a trigger which puts just a link to that image into a Cloud Pub sub. And that's basically a message queue. And there is a metric that can scale a Kubernetes cluster based on the length of that queue. So if there are like a lot of messages in that queue that were not processed, then it could add more nodes, so it can process them faster. And if it's not needed, there are no messages, then it can scale it down to save costs. And yeah, basically this Kubernetes cluster could run that torch serve Docker image, and that could do the inference and save the results to the Cloud SQL database. And let's see price estimate here. So here are the prices. Yeah, in all of these cases, I calculated with 100 milliseconds of inference time, which obviously going to change a lot. So this is just really a very rough comparison, but with a relatively small instance and the cheapest GPU, I would get around $11, so roughly cutting the cost in half. And this is the last one. This is like specialized Google AI platform solution. So this is like a serverless solution, and it's highly specialized for doing these kind of things. And the first part of the architecture would be the same, and then there would be a cloud function that takes out a bunch of messages from the messaging queue, creates a batch, and sends it for inference to the AI platform serving instance, and that would do the inference and send it to the and save the data to the database. And this is the price estimate for that, because this solution is built for this, and probably that's why it produces the best value for money. And so this also includes a highly theoretical 50 milliseconds of execution time on that cloud function that is making the batches. And as you can see, it would actually cost exactly the same as the prediction itself. So it seems like this is the cheapest option, and I think it would be also a pretty fast option, and this is basically infinitely scalable. So I think this is a really promising way of doing that. So basically I'm just writing it here that that to actually find out which is the best way to go, experiments would be needed. I might even do these experiments and write a fourth article about it if I will have some time, but it seems like that SageMaker and the AI platform, which are basically built for this, they look the most promising. So that's it. Thanks for the attention. And if you have any questions, I'm happy to answer.
First, I just want to say that was really great. Thank you so much for presenting. I really learned a lot. That was awesome. Thank you, Simon.
It's great.
Yeah, so now we're going to open it up to questions, you guys. If anybody has questions, feel free to ask. I actually have one kind of question from like a mentee standpoint. So I feel like you covered like a lot here. And I guess like in terms of, the whole project process, if there were like, I guess like if you could select one challenging aspect of it, what do you think was the most like challenging part of like building this project? Because I know you kind of touched on like deep learning, ML, computer vision. You also did front end, back end, and basically everything in between. So like, what would you say would be the most challenging aspect that you had to do here?
Yeah, definitely the cloud deployment. So it took me almost a month to get it right. So I didn't really have experience with it, so definitely that didn't have, but there is just like so many moving parts that has to work together, and deploying all those things, configuring all those things, and the permissions, so they can communicate with each other, they can save data, they can access each other's data. So that was definitely quite challenging. The other more challenging part, that it was a bit easier, that the WebSocket communication, I didn't even do the SSL and authentication part, so that as it is right now, anybody could connect to it and send messages and read the messages. But yeah, that was also not so easy to get it right.
Thank you.
I just had a...
Oh, sorry. Go on.
No, please go ahead.
Oh, yeah. I just had a quick question, Simon. Awesome talk. I was just wondering, in terms of like, you do a lot of the inference and everything all like on Amazon Web Services. Was that chosen? Like, I know you said there's kind of like a learning aspect where you chose some of that too, but was there also like a performance consideration versus like doing some more of that inference like on the Raspberry Pis themselves? Like, were you thinking that you could access like a scaling compute power of like the cloud by doing it online? Yeah,
like I think it would be probably possible to do the inference on the Raspberry Pi itself, but it would be super slow. So I think it has 1 gigahertz cores, 4 gigabytes of memory. This is the model with the most memory. I'm not even sure that this, especially with all these PyTorch dependencies, it would work with less memory than that. And I think it would take probably 5 to 10 seconds, maybe even more. So that's not really a way to go. Actually, there is a better way to do it than in the cloud. I didn't do this because I thought this is the best way. I did this because I wanted to work on these things, and I wanted to build a project that does inference in the cloud. So that was the biggest reason. But actually, I came across this idea later on because somebody wrote a comment to one of my Medium articles, and he recommended a device. It's basically like a Raspberry Pi with a built-in neural network inference chip in it. So that's manufactured by Intel. I'm not really sure about the name of it. But if you go to the articles, you can find it in the comments, and it's also not so expensive. I think around $200 or something like that, and that could definitely do this inference within like 100 milliseconds, and that would be definitely the best way to scale it up. Because I mean, it depends, because if your customers are buying that, and you don't have to pay for cloud compute, that's definitely good for you. But if you have to buy them, like 1 million of them, I'm not sure that it would be cheaper. Probably on the long term, yes, but short term, not sure.
Okay, cool. Thank you.
I was earlier just unmuting myself, say great talk, so.
So while kind of like waiting for, I know I bet people have a lot to think about. I have another kind of quick question. From like, I guess like if you had any advice for like mentees, so like given that this is like a mentee showcase, like a lot of people are just like starting their like mentorship. A lot of people are like in the middle of their project or like at the tail end. For those mentees who are just starting their project at SharpestMinds, could you talk about any tips that you have for, selecting a good topic and like, you talked about scope earlier, like what tips would you have for mentees who are just starting and deciding what project to work on?
Yeah, I think it's really important to build something useful. So that is not just some proof of concept or something, but like build an actual product that people can use. And I also found it very useful to create all kinds of visual materials, like the videos, like these drawings, or just pictures, and this kind of stuff. Because when you are interviewing and you write an article that takes 30 minutes to read, probably not a lot of people will read it. But if they go to your GitHub repository and the first thing they see a huge GIF which shows how your project actually works, it's going to take them 1 second and they get it what you're talking about. And if they are interested, they can get into the details with the text or with the code. So I think that's the two things I would say.
Thanks. Yeah, that's super helpful. So I think we'll give the chat a few more seconds, but kind of while waiting for people to think about questions, just wanted to share with, everyone on the chat, if you guys want, your project featured, or if you want to talk about, the project that you worked on at SharpestMinds, definitely let us know. We would love to kind of like share your work with the world to see all the cool and awesome things that you're doing. Like obviously like Simon's project is really cool. And yeah, this is just like a great space to kind of like get to know each other and like learn from other mentees in the community. So definitely let us know if you wanna have your project showcased next.
Yeah, thanks so much for hosting this, Amber, and thanks, Simon, for participating. I'm gonna hop off. I have a call coming up, and I gotta grab a bite to eat beforehand. So I'll leave you guys to it. Thanks again. Bye, everyone.
Okay, thanks for the attention, guys.
Well, I think that's all the time we have. But again, I just wanted to thank you, Simon, for your presentation today. I mean, I know I learned a lot, so we're super excited to see like what you do next. But yeah, thank you so much for being here, and thanks everyone for coming.
Okay. Thank you, guys. Nice
Thanks
day.
all.
Goodbye.